So thank you very much for the introduction and for the opportunity to speak here. So what I'm going to speak today about is joint work with Irina Mitrea from University of Missouri at Columbia. And it's part of a comprehensive program aimed at developing a layer potential method for treating boundary value problems for higher order elliptic differential operators. You know, many phenomena in physics are modeled by an elliptic partial differential operator, and one is typically interested in solving boundary value problems associated with this. I would like to point out that when the operator in question is of second order, a variety of tools have been very successful, have been successfully implemented over the years. These are boundary integral methods, calculus of variation methods, methods based on harmonic measure, and methods rooted in classical harmonic analysis. However, the situation is drastically different in terms of the successful implementation of this method for treating boundary value problems for higher order elliptic differential operators. In fact, until very recently, this method was almost, with very few remarkable exceptions, was almost absent from the literature of dealing with such problems. Alberto Calderon, one of the founders of the modern theory of singular integral operators, has called in the 70s for the implementation of the layer potential method for the treatment of elliptic boundary value problems associated with higher order elliptic PDEs. And I'm going to emphasize some of the success that we had, and point out to some of the challenges that one deals in the higher order setting. So to start with, I would like to just go over and remind how the layer, how the layer potential method has been so successful in the treatment of elliptic boundary value problems dealing with second order elliptic PDEs, see what the strategy is in there, and then compare, this with what one can do in the higher order case. Throughout the talk, we're going to be working in a very general class of domains. However, I'm going to address the geometry only at the end of this talk. So for the beginning, just think about a class of domains, so-called uniformly rectifiable domains. Is a larger class than Lipschitz domains, allows for much rougher geometries. However, it's still a class in which singular integral operator theory, Calderon-Zygmunt type theory, can be carried out. So let's consider a bounded reasonable domain in Rn and fix P between 1 and infinity. And let's look at the Dirichlet problem for the Laplacian with LP data. The Dirichlet problem for the Laplacian has three parts. One is consists of the PDE conditions in which we seek C2 function such that is harmonic in omega. So we can differentiate twice and make sense of the Laplacian. Boundary condition in this situation, we're asking that U restricted to the boundary. I don't think that so U restricted to the boundary in a non-tangential fashion is equal to F, and I'm going to explain the notation in a little bit. And the size condition, we're going to be requiring that the non-tangential maximal function of U is in LP. Okay? The non-tangential maximal function controls the boundary behavior of the solution of the problem, and in a way you can think of it that it plays a very similar role as the Hardy-Littlewood maximal function in the context of the Lebesgue differentiation theorem. So to put things in perspective, if X is a point on the boundary, gamma of X consists of all those points in the domain such that X minus Y is smaller than 1 plus kappa distance from Y to the boundary, where kappa bigger than 0 has been fixed. Okay? So this is the collection of all points in the domain omega, which cannot be substantially closer to the boundary without being close to the vertex. In the situation of the upper half space, gamma of X is nothing else but the straight upright cone with vertex X, whose aperture depends in an explicit fashion on the parameter kappa introduced in there. Okay? So So this is what we're going to call a non-tangential region associated with the point x. For a function u originally defined in the domain omega, we're going to set the non-tangential maximal function of u at the point x, where x is now a point on the boundary, to be the supremum over the cone of absolute value of u. Okay? So this is the non-tangential maximal function. And the non-tangential trace at the boundary, okay? We're dealing with a boundary value problem. The data is no longer continuous, so we have to be very precise the meaning in associating a meaning to the trace operator in this sense, and we're going to work with the non-tangential trace. So the non-tangential limit at the boundary is the limit as y goes to x of u of y, where y belongs to the cone with in the non-tangential non-tangential region with vertex at x. Whenever this is meaningful, and by this being meaningful, I mean two things. So in order to be able to approach x with points from the cone, it better happens that x is in the closure of the cone with vertex in the upper half case. This happens automatically, but as you deal with more complicated geometries, this may no longer be the case. Okay? The fact that x belongs to the closure of gamma x is so-called weak accessibility. And this is a geometry condition we're going to be assuming from now on. We're going to assume that our domain is weakly accessible sigma almost everywhere. And we're going to assume that the limit, so we're going to assume that the limit exists. Okay. So these are the three conditions for the Dirichlet boundary value problem with data in LP. And we're going to assume weak accessibility sigma almost everywhere on the boundary. Sigma here stands for the surface measure. And let's return to the PDE conditions. What is a mechanism of generating a lot of harmonic functions in omega? So this is the PDE condition has only to do with harmonic functions in omega. And I want to remind you here that if we are in 2 dimensions and we're looking at the identification of R2 with a complex plane, a mechanism capable of generating a lot of harmonic functions is the Cauchy operator. So if we look at the Cauchy operator of a nice function g defined on the boundary of the domain omega, such that the integral makes sense, this is going to be a holomorphic function in the domain omega. Okay? Well, the real part of a holomorphic function is going to be harmonic. So, this particular method, rooted in complex analysis, indicates that, we might want to consider the real part of the Cauchy operator acting on G, where G is a real valued function defined on the boundary of the domain omega, as a mechanism of generating harmonic functions if we are in 2 dimensions. It is a simple, geometric observation that this zeta here is nothing else but I, nu of zeta, where nu is the outer uninormal of the domain omega, so assuming that the omega is, nice enough that we can talk about something like this, and this sigma here is the surface measure on the boundary of the domain omega. With this observation in hand, so instead of this zeta, we're going to plug this in. We're going to look at this operator that we're going to call d. dg of z is the real part, and this is, I simply rewrote the Cauchy integral operator and I brought here everything, so that I have the distance between zeta and z squared in the denominator. Okay. Well, the real part, if g is real valued, this is real valued, so the real part is going to come in here, and the real part of this product of complex numbers is nothing else but the scalar product between nu, now regarded as a vector in R2, and zeta minus z. Okay? So in 2 dimensions, a mechanism to construct lots of harmonic functions, keep in mind that G is up to us, is via this formula. This is the classical harmonic double layer potential operator associated with the Laplacian in 2 dimensions. Inspired by the situation in 2 dimensions, in Rn we're going to consider the double layer of G to have a very similar formula. It's just that the power here, I'm going to take it to be n. And here we have omega n minus 1. Okay? So one more time, mu is the outward uninormal vector, sigma is the surface measure. The point x is in the domain omega. So this is going to be our mechanism capable of generating lots of harmonic functions for the PDE condition in the problem. Let me take one moment and observe that indeed this gives harmonic functions in the domain omega, even though we are in Rn now as opposed to R2, because in the integral kernel here, one can recognize easily the normal derivative of the fundamental solution of the Laplacian. Okay? So what we have here is derivative in the normal direction of the fundamental solution for the Laplacian. And keep in mind, so if I apply Laplacian in here, the Laplacian falls in the variable x. And taking normal derivative in y and Laplacian in x are commutative processes, the Laplacian is going to hit the fundamental solution, but x is inside the domain omega, while y lies on the boundary, and as such, you know, we're going to get 0. So this is a harmonic function in the domain omega. Regarding the boundary conditions and the jump conditions, the boundary behavior of the double layer potential operator, I'm simply going to say here that the powerful Calderon-Zygmund theory, collection of results obtained over the years, yield the fact that for each g in LP, the non-tangential maximal function of the double layer of g is in LP, and we have uniform estimates. And for each g in LP, when one restricts the double layer of g non-tangentially to the boundary, one obtains 1/2 identity plus kg, sigma almost everywhere on the boundary, where k is the boundary version of the classical harmonic double layer potential operator, is the principal value integral operator. Okay, so here, p, so it has a very similar form as the double layer, but p is now on the boundary. And in fact, the very existence of this principal value limit is actually quite a sophisticated question. Okay, so it comes as a result of the Calderon-Zygmund theory and T of 1, T of B theorems established by Kochman, McIntosh, Mayer. But let's assume this for the moment. So, you know, just think about as a body of techniques that have been developed that guarantee these two conditions. And at this point, we have a mechanism of generating harmonic functions. They are of the right size. Remember that we look for solutions of the problem such that the non-tangential maximal function of u is in LP. So if we take the double layer of any LP function, this is going to satisfy this condition. And this particular jump formula is going to help us understand how we should choose G such that the boundary condition in the original problem is going to be satisfied. So I have rewritten here the boundary value problem that we have started with. And our strategy is to consider U to be the double layer of G for some G to be determined. This is satisfied because this is a mechanism to create harmonic functions. This is satisfied because we have non-tangential maximal function estimates for the double layer potential operator. And we know that dg restricted non-tangentially to the boundary is 1/2 identity plus kg. And this better match the Dirichlet data F. So the boundary condition becomes 1/2 identity plus kgf. And if the circumstances are right, one is able to invert 1/2 identity plus k and write the solution of the problem as the double layer of the function g, which is 1/2 identity plus k inverse of f. Okay? So this is the typical strategy employed for dealing with the boundary value problems for the Laplacian, and you know, this typically works for second order elliptic systems as well. However, the success of the strategy hinges on one's ability to invert the operator 1/2 identity plus k on LP. And this is an issue which is sensitive to the smoothness, flatness of the boundary of the domain omega. If the domain is the upper half space, recall that in the very writing of the operator k, the kernel was of the form nu of y minus x all over x minus y to the power n. But if we are in the case of upper half space, x and y are both on the boundary, the uninormal vector is going to be perpendicular on the chord. This is 0. So K is 0, and 1/2 is certainly invertible. Okay. So the flatness of the upper half space, trivializes the issue in this setting. Okay. This is in a nutshell the layer potential methods for second order elliptic boundary value problems, and I just want to spend a few minutes giving pointing out some of the historical developments. We go back to the work in the late 70s of Alberto Calderon, who has proved the L2 boundness of the Cauchy integral operators on Lipschitz curves with small Lipschitz constant. Immediately, this had application to PDEs. Fabio, Diet, and Riviere were able to use Calderon's result and prove that if omega is a bounded domain of class C1, then the operator K is in fact a compact operator from LP into LP for any P between 1 and infinity. As such, the operator 1/2 identity plus K, which we are seeking to invert, becomes a compact perturbation of an invertible operator, which is Fredholm with index 0, very close in spirit to the invertibility condition we seek. Koifman, McIntosh, Meyer were subsequently able to remove the smallness of the Lipschitz constant conditioning here, and as a result of their work, the operator K is a bounded operator from LP to LP for any P between 1 and infinity. I want to, one more time, focus on Fabio Diet Rivier's result, because this is going to be the spirit in which this is going to be the focus on the lecture today. The ability to carry out a Fredholm type theory for layer potentials for higher order elliptic PDEs. So we're going to look at a similar approach, and in the case of higher order, we're going to look at conditions which are going to make the operator K compact on LP. I want to just point out that in general, if omega is merely Lipschitz and not better than that, then the operator K is not compact. Even the presence of a very single corner, prevents K from being compact on LP. Yeah. So in fact, for many reasons, P equals 2 is, from the point of view of the spectral radius of the operator K, P equals 2 is sort of the worst case scenario. All right, even though, this is an argument not based on Fredholm theory, I wanted to point out here that Greg Verkota, a student of Fabes, has proved that if omega is Lipschitz, then 1/2 identity plus K is in fact invertible on L2, and his techniques rely on so-called relic type identities and estimates. So K is not compact, however, 1/2 identity plus K is invertible via a different method. So the layer potential method for second order elliptic PDE has been very successful. Dalberg, Koenig, and Verkota have been able to treat successfully the Dirichlet problem for the Lamé system. Yeah, well, in just some particular situation. So there is still, even in the case of Lipschitz domains in 2 dimensions, the spectrum of these operators is not completely understood. So there is still an open question, the so-called spectral radius conjecture, which asserts that the spectral radius of the operator K on any bounded Lipschitz domain on the, when acting on the space L2 is strictly less than 1/2. There are some. So the Lamé system is a second order elliptic system that models elasticity. Okay, I can write this down, but for the moment, just think about it: a second order elliptic system with constant coefficients, that model the Hooke's law of elasticity. Okay, so Fabes, Koenig, and Verkota, and Dalberg, Koenig, and Verkota have treated boundary value problems for the Stokes system, and then much more is known right now. Other P's, other function spaces, even though, as I mentioned, there are certain questions which are still yet to be understood. They are very difficult, but people don't regard them as something that stops the theory in place, from moving forward. So. I would like now to move towards higher order elliptic so to change the setting to higher order elliptic PDEs. So let's consider a higher order.
So does all this go right through for secular equations which are uniformly elliptic if divergence form, for example?
Well, if you want to have variable coefficients, one should be a little bit more careful. But under a lot more is known. So these problems have been studied, for constant coefficients, variable coefficients in the Euclidean setting, in Lipschitz subdomains of Riemannian manifolds. So a lot is known.
But is it pretty much follow what you did said for the Laplacian, or do you have to have more?
As heuristically, it follows the same blueprint as in the case of the Laplacian. Things are a little bit more complicated in the setting of a Riemannian manifold. You don't have, explicit understanding on the fundamental solution. You just understand the principal part, and I mean, so there are certain difficulties that that have to be overcome. It's just that overall, this method has been considered tremendously successful because, in principle, it does not distinguish between the case of a single equation and that of a system. So, it's not based on positivity or maximum principle. Also, it does not distinguish in principle between the case of the Dirichlet problem and the Neumann problem. The operator that you need to invert in one is the dual of the other one.
So maximum principle is not used here.
No. So these are methods that don't rely on. So this is what allows them to be successfully implemented for systems. So, I'm turning to higher order. So I'm going to consider the case of higher order constant coefficients. So I'm considering here, let's say, capital M, M by M system of homogeneous differential operators. So here, alpha is a multi-index in Rn of length little m. So the operator has order 2m, where this is the partial differential operator associated with the multi-index alpha, which has components alpha 1, alpha n. We're assuming that the coefficients are constant, complex valued, possibly matrices. So this covers the case of systems, and we're assuming ellipticity. So we're looking at the Dirichlet problem for this system in Rn. So we're going to have a PDE part, we're going to have a boundary condition part, and we're going to have a size part, much like we had in the case of the Laplacian before. So we're seeking null solution of the operator L in the domain omega. We're prescribing derivatives to the boundary restricted non-tangentially up to order m-1. So gamma here is a multi-index of length less than or equal to m-1. We're prescribing all these derivatives at the boundary, and these are f gamma. So this is the collection of the f gammas, is our Dirichlet data in this setting. And we're asking for the non-tangential maximal function of the gradient of order m-1 of u to be in LP. Before I go any further, I would like to say, and this is something I'm going to revisit in a second, is that one expects the collection of f gammas to satisfy certain compatibility conditions. They cannot be quite anything, because ultimately they're going to be restriction to the boundary of derivatives of various orders of this function. However, in sharp contrast to the situation with the literature existing for the second order case, in terms of implementing a systematic layer potential method for the treatment of such problems, these are the two remarkable exceptions that I mentioned earlier. So Agmon, Shmuel Agmon in the late 50s, in a really truly pioneering work, he has proved the well-posedness of the classical Dirichlet problem. This is continuous boundary data and Hölder data in C1 plus beta domains in R2 for beta bigger than a half. These are all single equation with real constant coefficients. These are very smooth domains, C1 plus beta, and the data is very smooth as well. Cohen and Gosselin, many years after, were able to prove the existence of the solution of the Dirichlet problem with data in LP for any p between 1 and infinity. However, for a very specific higher order elliptic differential operator, that is the biharmonic, in C1 domains. So here, the regularity of the domain lowered a little bit. We're still in 2 dimensions, and we're looking for the Dirichlet problem for the biharmonic operator. And this was done through a layer potential type approach.
Well, I noticed that your conditions require some kind of homogeneity in your operators. Is that just convenience, or do you?
Well, you know, so it's a very good question. What happens otherwise? But things were not understood even in this setting. Okay, so that was
I would think if you added a lower order term, elliptic term, that would be helpful, but maybe not.
So you know, I mean, I would imagine that certain things can be done, but I don't think that, you know, they have been neither done nor understood yet. So it depends on the nature of the lower order term. All right, so these are, you know, we're looking at the few exceptions existing in the literature, and you know, this has been, so there is a big contrast between the situation of second order and higher order in terms of this particular method. So, yes?
Is there any insight that we would gain, or I would gain, by understanding why the term layer, the double layer potential?
Well, my understanding, yes.
I mean, where does that come from?
Well, so this comes from physics, you know, so my understanding is that, you know, these notions of single layer and double layer, you know, were introduced by mathematicians that were working on problem from physics, and it has to do with the fact that when considering the Neumann problem, they were looking at a boundary value problem where they had one layer of sources distributed over the sphere, and, you know, that led to the concept of single layer, and then you had 2 layers of charges over the sphere, and this led to the, so it's all rooted in physics. I mean, they don't offer much mathematical insight. All right. Well, so in order to describe some of our work, you know, I want to point out that, you know, our work came in batches, you know, so we recently published a book that deals with you know, the systematic treatment of boundary value problems for higher order elliptic PDEs in Lipschitz domains. But what I speak about today is the result we obtained 2 weeks ago, you know, so it's about the treatment of these problems in much more general geometric setting, that of no, not yet. Before I go any further, you know, let me return to the issue of compatibility conditions. So recall F gammas, the collection of F gammas indexed over gamma of multi-indices of length less than or equal to m minus 1. I'm going to put them in a collection that I call F dot. So the dot stands for, you know, this array. And the compatibility condition that one expects out of the Dirichlet data is that once you take a tangential derivative of a component of the array, this expresses as a linear combination of the components of the array at the next level. Here, Ej stands for the multi-index which has zeros except the j component where we have 1. And the coefficients are components of the uninormal vector. You know, we have to deal, you know, with, you know, differentiating only in the tangential direction because these are objects which only live on the boundary. Okay, so these are the natural compatibility conditions. We're going to say that the array of that satisfies the compatibility conditions, provided this is true for any multi-index of length less than or equal to m minus 2, so that we allow for the next level to still be within the array. Okay. What is going to be our natural LP space? Well, you know, let me decorate this with a dot as well. P stands for integrability. M minus 1 here is to remind us of the order of the operator. The higher order differential operator has order 2m. And 0 is here to denote that, you know, there is no extra smoothness. We deal with also more regular versions of this space. So we can have 1, for instance. So this consists of arrays that satisfy the compatibility conditions such that all their components are in LP. I would like to point out, though, that a lot of the components in the array have better regularity than the definition indicates in a trivial fashion, because if I take an extra tangential derivative, this combination here is going to be in LP. So as long as I'm not at the top level, when the multi-index has length m minus 1, I can still take a tangential derivative and land in LP. So this is... No, so I think that I think that these are the right function spaces, you know. So this is the natural equivalent of, I mean, the natural counterpart of LP in the higher order setting. We're also going to need a new concept of trace. See, if I have a nice function f defined in the domain omega by trace m minus 1, I'm going to understand the non-tangential restriction to the boundary of all derivatives of order less than or equal to m minus 1. So now the boundary value problem formulates in a very similar fashion as the one for the Laplacian. We're seeking null solution of L such that trace m minus 1 of u is equal the array f dot. Okay. All right. So I would like to point out one of the difficulties or one of the challenges that one actually encounters in the higher order setting. We're going to consider a bilinear form acting on two nice functions, u and v, in the domain omega, something that looks this way. These are some coefficients, and we're going to say that b is associated with L, provided that if we integrate by parts as to move all the derivatives on v onto u, at the end we end up with a solid term, which looks like LUV, plus whatever the penalty, the boundary integration by parts penalty is, you know, these are the boundary terms. Okay. All right, so we're going to set, just because it's very hard for me to explain what a double layer is in this higher order setting without putting a super technical and you know, a hard definition to understand, I'm going to say formally that the double layer acting on the array f dot is the boundary terms obtained via this process when you replace u by Ex, where Ex is the fundamental solution with Paul at x. E is the fundamental solution of L. And whenever you have d gamma v, you're going to replace that by the component gamma of the array f. So this is the recipe. You have a bilinear form associated with L. You're going to perform this. We're going to look at the boundary integral. And this is what we're going to call the double layer. Okay? So one of the difficulties is apparent here. You know, you give me a bilinear form. Well, there are many ways to integrate by parts. So I'm going to have many ways in which I can write my double layer. Okay? And then reading of functional analytical properties of that writing, the writing may influence your ability, how easy it is for you to read these properties of it. To make things even more complicated, well, there are infinitely many bilinear forms associated with a higher order elliptic differential operator. Each one is going to give rise to a different double layer. So I have infinitely many double layer potential operators. And in solving the problem, I would have to look for the right one, the one that I'm actually able to invert. Okay? All right. So before I go any further, I want to show you a concrete example. So let me consider the case of the Laplacian cubed in 2 dimensions. So m is equal to 3 here. So I have arrays of length less than or equal to 2. So I have multi-indices now in R2 of length less than or equal to 2. These are all. This is how my array f dot looks like. And there are many bilinear forms associated with this operator. Each one gives rise to a double layer. Which one? The one that I'm showing you right now is the nicest of them all from the point of view of the functional analytical properties. So yes. So, and keep in mind, this is for a very specific operator, Okay, and this is the nicest of them all. This is the one that mimics in spirit what happens in the case of the Laplacian. So this is the equivalent of the classical harmonic double layer potential operator. Namely, if your domain is smooth, this operator, this is the boundary version of it is going to be a compact operator on LP. Okay, it's so it's a very good question. Yes, so this is a very good question. In the case of higher order, this has not been completely answered, but based on our experience with second order, at which you can, second order systems, you can already see the manifestation of this principle. In the second order case, we know for sure that there is always just one. So we expect that this is the case in the higher order setting as well. We do not have a proof yet. But so this is the best double layer for the tree Laplacian. So things are quite difficult. So these are the components of the array. These are components of the uninormal vector, and these are packages of the derivatives acting on the fundamental solution. Note here that we have as many as 5 derivatives acting on E. Okay. Well, the theorem that I wanted to say, that I wanted to mention is the first one that deals with the ability to build the Calderon-Zygmunt theory in this setting. So if omega is a bounded uniformly rectifiable domain, then one has non-tangential maximal functions for the double layer acting on any Whitney-Lebesgue array LP. And we have similar jump formulas as we've seen in the case of second order. Okay? The key tool in this setting is a sharp divergence theorem on uniformly rectifiable domains capable to handle non-tangential traces. So this is, in this business, it's key that you are able to integrate by parts null solutions of nice functions, but that you only know the non-tangential behavior at the boundary. So while the classical de Giorgi-Federer integration by parts divergence theorem, was handling rougher domains of locally finite perimeter, this was done only for smooth vector fields of compact support. These are not appropriate for PDEs, where many times, this is too much to ask of your solution of the PDE. So one needs to add a little bit more structure to the geometrical conditions and relax the smoothness assumptions on the vector field on which you apply the divergence theorem. All right, so one has the size conditions, and we understand the boundary behavior. Okay, so now, once we understood the boundary behavior, the matters becomes as before: 1/2 identity plus k dot g dot equals f dot. When are we able to invert this operator? Okay. So this brings me to the second result. If omega is a bounded regular Sem-Skenik toroid domain. So what I want to, and I'm, if I get a chance, I'll touch this particular topic. If not, think of regular Sem-Skenik toroid domains being domains which generalize the class of C1 domains, or the class of domains which are Lipschitz and uninormal in VMO, in the Saracen space of vanishing mean oscillations. The uninormal, has vanishing mean oscillations. Is the generalization of the C1 case.
We could just think of Lipschitz, right?
Lipschitz, no. A Lipschitz domain is not necessarily regular SKT. Even if you have a sector, the uninormal, has to be a lot more regular, or a little or a lot, yes. So the oscillations of the uninormal vector have to be vanishing. Okay? So in this situation, which generalizes the C1 case, for any p between 1 and infinity, the Dirichlet problem with LP data is well posed. And I see now that I forgot to put a crucial I forgot to add 2 crucial hypotheses in here. This particular theorem is valid in R2, and this particular theorem is valid only when dealing with the case of a single equation with real coefficients. So I went a little bit ahead of myself and forgot these two. So this is a two-dimensional result, one more time, and this is for a single equation with real coefficients. So the Dirichlet problem with LP data is well posed. Well, we want to apply the mechanism we've seen before in action. We want to invert this operator whenever possible. But we've seen that we have lots of double layers. You know, the success to invert this may depend on which double layer we choose. Well, you know, our quest is going to be to find a good one for which, you know, this program can be carried over. So we're going to try to employ Fredholm theory, as I said. So we need that K dot is compact on LP. So this brings us to a natural question. What are compactness criteria for this type of singular integral operators? We're looking here at the classical harmonic double layer. I decorated with the Laplacian just to remind you that we're dealing with also other layer potentials. This operator is compact on LP. You know, we've seen from the work of Fabio Diet-Riviere when the domain omega was of class C1. It turns out that that result can be generalized to the situation of regular SKT domains. So when we have the classical harmonic double layer potential in this particular geometry, that is compact. Another recent, relatively recent result of Steve. For compactness, no, no. And from the point of view of boundness, P equals 2 is the key case because these are Calderon-Zygmund operators, yeah. So.
And the reason to, I know people like to look at P spaces, but they're useful in nonlinear equations. That's what we.
So the reason for which people look at other.
You immediately put LP spaces. That's everybody does. I think.
I say.
I'm asking why. I mean,
because the.
One is L2, there's an infinity. I don't believe in the ones in between.
Well, I do. No.
Okay, all right.
So.
Maybe not the numbers.
You know, so even in the case of second order, if you want to solve the Dirichlet problem with LP data, you cannot quite solve it for any LP. You know, the problem is that the range of well-posedness is 2 minus epsilon infinity, and this is sharp. For any epsilon bigger than 0, you can find the Lipschitz domain such that the 2 minus epsilon.
Maybe the reason I ask is in the old Calderon-Zygmund theory, now basically L2 and then some little bit more gives you LP.
That's
So
true.
I'm trying to understand if I should just think of this equals 2 and then that's what it
No, so the issues are different, you know, because you know boundness is it's one ingredient, invertibility is a different one. It's a separate thing, yes. So P different from 2 may present its challenges, you know. So.
Are you going to say a word about this compactness?
Yeah. So this is you know. Based on these blueprints, Steve Hoffman, Marius Mitrea, and Michael Taylor were able to prove essentially what is an optimal compactness criteria for this type of singular integral operators. If omega is a bounded regular SKT domains, and your singular integral operator has this particular form, okay? So we have here K, which is a C infinity function away from the origin, even and homogeneous, positive homogeneous of degree minus n. And you have this inner product, P minus Q, the chord with the unit normal vector, and the density integrated versus the surface measure. This is a compact operator on LP.
Are you going back to second order here or not?
No, this is in general. This is a compactness criteria in general. If your integral operator looks this way, and if your geometry is this way, for sure your operator is an integral operator that is compact on LP.
How do you show it's compact? By finite dimensional approximation or by
well, you know, so if you want to think about it, I mean, you know, the analogy that probably is the easiest to understand is the situation. Let's assume, because for instance, K associated with Laplacian follows this blueprint. This is a particular case of this one. So let's assume we have the situation of a C1 domain, and I would like to show that K is compact. So this goes back to the procedure, the design by Fabio, Dait, and Riviere, and overcoming it in this more overcoming obstacles in this more general geometry. What Hoffman, Mitrea, and Taylor have done, is to show so if I have, for instance, the case of the Laplacian in C1 domain, I can approximate the C1 domain via C1 plus epsilon domains, such that the operators, the boundary layers, converge in a strong operator norm to the one there. Because in C1 plus epsilon domains, your operator is going to have a weakly singular kernel, and compactness is going to be, comes from there. In the C1 case, you no longer have weak, yeah. So that's the procedure. So this is what we, this is a compactness criteria. Okay. So my goal is to find all these double layers such that all components of K dot are of this form. And one observation is that if I have a function in R2, this is where the restriction to 2 dimensions comes from, which is C infinity and homogeneous of degree 0, then if I take its tangential derivative, this is going to have the desired form. Okay? It's going to have this inner product multiplied by a C infinity function, which is even and homogeneous of degree -2. So I'll quickly walk you through the argument, So let's take a point in R2. Let's set P star for the orthogonal of the vector P. Then for any PQ, it's easy to see that the scalar product between P and P star is 0, and the scalar product between P and Q is the scalar product between P star and Q star. And for any P which is non-zero, and for any Q in R2, we can always decompose Q along P star and P with these particular coefficients. Okay? So now let's take our function, which is homogeneous of degree 0. And by the homogeneity of degree 0, it means that f of Tp equals f of P for any T. And differentiating with respect to T is gonna imply here that the gradient of f is at P is because it's gonna be perpendicular on P. In 2 dimensions, the tangent unit vector is nothing else but the star of the unit normal vector. So let's take the tangential derivative of this homogeneous function of degree 0. This is the tangential direction scalar product with the gradient in Q. Taking gradient in Q, we can simply pull out a minus and take the gradient of f. Okay. Now let's decompose the gradient of f along the directions P minus Q star and P minus Q, according to the recipe we've had before. So instead of tau, I wrote nu star, and I take this and decompose it along the direction P minus Q and P minus Q star. Because of the homogeneity condition of degree 0, this particular term drops off. Okay? And this is a scalar which pulls out in front of the inner product. And at this point, we're left with new scalar product of P minus Q, both with stars, and we can erase those. As such, the form of our kernel is this one multiplied by this quotient. F was homogeneous of degree 0, and the simple homogeneity calculation here shows that this is homogeneous of degree -2, exactly as desired. So whenever we have the tangential derivative of homogeneous function of degree 0, that is going to lead to good kernels. Okay. So to keep the story short, we're going to, if you try to solve the boundary integral equation, this is going to lead to integral operators which are the harmonic double layer plus integral operators whose kernels are tangential derivatives of 2m minus 2 derivatives on the fundamental solution of the operator E. And this would be the end of the story if this quantity would be a homogeneous function of degree 0. Because tangential derivatives of those in 2 dimensions will give rise to good type of operators. But that is not the case. And I have just a couple of fun examples, and I'll stop here afterwards. So let's consider the biharmonic. So m is equal to 2 in this situation. This is the fundamental solution, fundamental solution for the biharmonic operator, the classical radially symmetric one. And we have to look at derivatives of order 2m minus 2. This means 2 times 2 minus 2, that's 2. And let's look at the situation when we take one derivative in x and one derivative in y. We compute that. This is good. This is a homogeneous function of degree 0. For that reason, 1, 1 is good, but 2, 0 and 0, 2 are both bad because when you differentiate twice with respect to x, the logarithmic term, survives, and that breaks this is not a homogeneous function of degree 0. So the same situation happens with 0, 2, so these are both bad. However, there is a little bit of good news that, well, if you take the air difference, the logarithmic term drops up and you do get a homogeneous function of degree 0. Well, the moral of the story is that out of all bilinear forms associated with the higher order elliptic PDE, one needs to identify the one such that, much like in the situation of the biharmonic, the bad multi-indices combine in a good way. Okay? And in the case of the biharmonic, this particular bilinear form has been identified by Agmon. This is the so-called Agmon's distinguished bilinear form. This is how it looks like. Okay. However, this job needs to be done in the general situation. Before I go any further, so if you take this particular bilinear form, let me show you how the double layer looks like. So I'm looking at the 0, 0 component of the double layer. The double layer k dot takes arrays into arrays, so we're going to have to look at all components. This looks at the harmonic double layer. The tangential derivative, this was a good multi-index, so this is a homogeneous function of degree 0. This is going to be a compact operator. The component 1, 0, again, I have the harmonic double layer, which is fine. I have a good multi-index, and I have the bad ones, but combined in the good fashion, in the way where they cancel, their logarithmic presence. And this is K01, which has a very similar behavior. And, well, the crux of the matter, that is the fact that the good choice of bilinear form is always possible, and there is a certain recipe associated with it. You can always write your double layer as the classical harmonic double layer acting on a component of an array, the tangential derivative on, these are packages of 2m minus 2 derivatives acting on the fundamental solution, particularly cooked up in such a way that the bad multi-indices happen, cancel out. With this, I think I'm running out of time, so the only thing that I want to point out, I want to say, maybe put this picture up one more time, just to emphasize the geometry. C1 domains are strictly included in domains which are locally given as upper graphs of functions with gradients in VMO intersected with L infinity, which is precisely the class of Lipschitz domains with VMO normals, which is precisely the class of Lipschitz domains intersected with the regular SKT domains that we've been talking about here, which is strictly included in regular SKT. These are the two-sided non-tangentially accessible domains. These are domains that have been introduced by Jerison and Kenning as a challenge, as a response to a challenge by Stein to study the most general setting in which non-tangential in which you have Fatou theorems for harmonic functions, intersected with Alford's regular domains, and this is a strict subset of the class of uniformly rectifiable domains. So this is the class where we have a satisfactory Calderon-Zygmunt theory. However, it's very difficult to invert operator in this setting, so the Fredholm theory happens at this level. For regular SKT domains, one can choose in 2 dimensions, one more time, 2 dimensions. So a lot remains to be done. A lot is not yet understood even in the homogeneous setting, and but we hope that this opens the door for the systematic treatment of this problem in this fashion.
Thank you very much.
Thank you.